Hello, ladies and gentlemen. Root Beer here. Thank you for joining me as we finish off the 2009 Hypatia contest. We're on question 4, and hopefully you guys have downloaded a copy of the contest or otherwise tried this one for yourself. We're going to go through it together now. So question 4, the last question here. We've got 3 parts here. A solid right prism, A, B, C, D, E, F, has a height of 16, as shown. Also, its bases are equilateral triangles with side lengths 12. Points X, Y, and Z are the midpoints of edges AC, BC, and CD, respectively. Determine the lengths of XY, YZ, and XZ. Okay. Now, it's not often we get some spatial geometry in question 4. I'm just going to read through the other parts just so I understand where we're going with this. This is usually a good idea to do on questions 4 on the Hypatias and Galois. B part. A part of the prism is sliced off with a straight cut through X, Y, and Z, so cutting along these dotted lines almost. Determine the surface area of the solid C, X, Y, Z. So if we chop off this corner, as shown, determine its surface area. Alright, we'll probably have to use the lengths we calculated there. Now C, the prism ABCDEF in part A is sliced with a straight cut through points, some different points, so we're sort of ignoring what happened in B, but through points M, N, P, and Q on edges DE, DF, CB, and CA. Okay, just like we've got shown. If DM is equal to 4, DN is equal to 2, and CQ is equal to 8, determine the volume of the solid QPCDMN. So the volume of this chopped off bit. I think that's kind of nice. We do a length, then we do area, then we do volume, but I'm not seeing really how many of these questions are connected. I think it's just ever more challenging three-dimensional geometry. And as an aside, I'm terrible with the spatial geometry and the 3D geometry problems. I'm quite bad at them. And as a result, I try and get my hands on them whenever I can. Because if you recognize that you're bad at something, those are the questions to practice, and those are the things you go look up. What's the general theory of these types of, whatever. I welcome the challenge. I'm not going to be afraid of it. I do apologize if I somehow goof this up, but I'm not so good with the spatial reasoning on the contest problems. Anyway, back to A part. We just want to figure out lengths X, Y, and Z. All right, well, let's draw a picture here. So we've got an equilateral triangle on top, and X, Y, and Z, we were told that these are midpoints. Okay. So now midpoints here, we got C, and then I think it was X, Y, and Z here, and D, and this one would have to be A, and this one over here is B. Okay, so we want lengths X, Y, Y, Z, and Z, X. Well, what have we got? Well, notice that, and I do need to copy down, it's E and F. Okay, so EF. So notice, triangle ABC is equilateral. And both ACDE and BCDF are rectangles. Okay. So what we can do, I'll do the rectangle ones first, and then we'll talk about the equilateral triangle lengths. But if we have ACDE here, and we can get A is here, and Z is here. We know this is 16 and this is 12. So that tells me we've got 6 and 6, 8 and 8. And take a look here. XCZ is right angled at C. So we see that xz squared is going to be xc squared plus cz squared, but I know each of these lengths. So I get 6 squared plus 8 squared. That's going to end up being 100, and xz is going to be equal to 10. Now, I think we can say probably similarly yz is equal to 10. I don't think we need to show that. If you think you need to show that, by all means, write that up, but it's the exact same argument. So similarly, yz is equal to 10. Okay. Now, how about y or xy? So we've got midpoints here, and A, B, and C up here. Now we get 60 degrees here, we get 60 degrees here, we get 60 degrees here, and these guys are midpoints, so 6 and 6, and 6 and 6. Well, you could say something like by cosine law if you wanted to. We could calculate, so by cosine law, xy squared is, so we're using a lot of squares and things like that. So xy squared is xc squared plus cy squared minus 2 xc cy times cos of 60. So this argument will work fine. You could also probably say, because these are midpoints, this xcy is going to be a similar triangle, and this will be 6. But let's carry out the calculation. Xy squared is 36 plus 36 minus 2 times 36 times, well, what's cosine of 60? It's 1/2. So this is 36. Xy is equal to 6. And so I would box each of my results just so it's quite clear. You can also put a therefore statement, but we've done part A here. Okay. Now I've clearly run out of space, so we're just going to move over when we talk about B. And we're going to redraw the picture. So now we take this the slice, we slice through x, y, and z. We take that off, and we want to figure out surface area. Well, it's a corner here. It's clearly a tetrahedron, not an equilateral tetrahedron, but it is a nice little 4 sides, 6 edges, that sort of thing. And so the surface area of CXYZ is the area of triangle CXZ. Hey, that's a right angle triangle that we've already seen. Plus the area of CYZ. Oh, hey, that's another right angle triangle, exact same copy. Plus triangle XYC. I'll change it to CXY. We've been putting the C's in front the entire time. CXY plus triangle XYZ. Okay. So, so C XZ, we already saw, has a base of 6, height of 8. So this is going to be 1/2 6 times 8. This one here, same sort of thing. Y, C, Z, 8, 6, and it's also right angled. So this is 1/2 6 times 8. This one here, it's equilateral of side length 6. So how do we calculate the area of an equilateral triangle? Well, it does happen to be isosceles, so we can draw a perpendicular here, and you can either say, well, it splits the base into 2 3s and work out that this is going to be 3√3 from here, or you could say, well, gee, it's 60 degrees, 90. It's going to be a 30, 60, 90 triangle. Those always have a ratio of 1 to √3 to 2. So whatever this chopped length here is, we just √3 times that. So it's going to be 3√3. So this is 1/2 base, which is 6, times height, which is 3√3. And maybe a slightly bigger diagram, maybe with a sentence or two, would really help us out there. Now XYZ. That's not the easiest thing to see, but we'll take a look. XYZ, we know from A A was all about calculating these lengths. So from A, we know it's 10, 10, and this length here was 6. Okay, well, what are we to do? It's isosceles. So we can split the base here. And now the height here, the height squared is going to be 10 squared minus 3 squared by Pythagoras. If you wanted to, you could give this a name like, I don't know, H. Talk about ZH or things like that. This is going to be 100 minus 9 is 91. So this is going to be root 91 here. So we get plus 1/2 6 times root 91. Is that, yeah, 100 minus 9 is 91. Okay, it's just weird to see a root 91 in a problem. Anyway, 1/2 6 times 8 plus 1/2 6 times 8 is just going to be 6 times 8, which is 48. The 6 and the 2 cancel out, we get 3, so this is going to be 9 root 3. Then the 1/2 and the 6 cancel out, we'll get 3 root 91. Which seems quite awkward. I will absolutely agree. I usually go in expecting some more elegant answers. It's exact. It's just the root 91 just seems out of place. And, you know, you've got 3 terms, 2 separate roots. I would have expected things to clean up a little bit better. But then again, it is a weird sort of lopsided tetrahedron. So, and none of our calculations, nothing we really had to stop and think, gee, what do I do here? I mean, we had an isosceles triangle, root 91, equilateral triangle, right angle triangles. This all was not hard to do. Just, you know, the answer's a little weird. Okay, but it's going to be correct, so we'll move on. And now C part was about a volume. I'm just going to reread C part because it's been a while, so I'll just refresh my memory. So it's not using the x, y, and z from before. That's okay. So our equilateral triangle prism is sliced with a straight cut through M, N, P, and Q. And if their picture is anything to go off, this isn't a nice little rectangle. It's a weird trapezoidy figure. Okay. And it's on DE and DF and so on. Okay, so we know only a little bit here. DM is 4, DN is 2. But we do know DEF is a equilateral triangle, so 30 degrees here. Not 30 degrees, 60 degrees. So we could probably figure out MN. And then CQ is 8. And we don't know what CP is. We do have the 60 degrees here, but one side length and one angle is not enough. But we are told it's a solid right prism. So these equilateral triangles are right on top of each other. They're right above each other. So if we can work out with the DMN and that 60 degrees, if we can work out this triangle, I'm betting that CQP and QC and P and CPQ are the same as DMN and DNM as angles. So then we can figure out that. But then the question would be, so right now I'm trying to figure out a plan of attack. The question would be, how do we calculate the area of this figure? Because I don't even know what to call that shape, quite frankly. So I would not know how exactly to calculate it. So what do we usually do? What do we do on Waterloo contests when we have to calculate? Well, we don't usually have to calculate volume, but when we have to calculate area, if you watched any of my other, usually that comes up on like the Kalian format. But usually there'll be questions on the multiple choice contests where they have you do things like calculate the area of this shaded region. And it's a circle that's missing a particular triangle, like a right angle triangle or something in it. And so the way you do that is you realize, oh, the shaded area is just a circle with a triangle cut out. And so now I'm imagining the same principle as here. I'm just trying to figure out what exactly it is. Okay, so let's all look at the shape together. Because if we can figure out a plan of attack, a way to understand the spatial orientation here. So, I do know CQ is 8 and then DM is 4. If my sort of similar triangles, common angles idea tends to work out, it's sort of like everything's narrowing. Now, it doesn't narrow to a point. It's sort of like... this is so hard because if we could flip it, I think this is a tetrahedron with its top pointy bit chopped off. Right? I think these lines should all eventually converge to some point. And then if we can figure out where that point is and what the height is, so we'd extend the CD down to some point, say G down here or something like that. That would have a particular height. And then area of a tetrahedron is 1/3 base area times height length. So that's roughly an idea. How we calculate that G and that height, we'll deal with that in the future, but tricky. Okay, let's get back to some of the things I do know. So we'll redraw the picture. I think I can figure out at least that bottom triangle. And then probably some sort of hand-wavy argument about angles will get me the top triangle. So we've got, I'll use the faint yellow for this. I got a little something like this. And basically, I think it's just going to be a bigger version up here. So what I was saying, I think that if we sort of extend it down, we'll reach some point G down here. And then this sort of looks like, if we flip it over, it looks like just a very tall tetrahedron, and then we chop off the top, which is another smaller tetrahedron. So I think this area is a tetrahedron minus a smaller version of that tetrahedron. That's the current plan. I think that's what we're going for here. So we got D, E, F, I think it was M here, N here, P here, Q here, C. I don't imagine we'll actually have to be using A and B, but there's everything. We know this is 8, this is 4, this is 2. Okay. So, if I take a look, we got 60 degrees here at D, M is 4, N is 2. Okay. I think cosine law. Maybe this question is just geometry involving things like cosine law, because Pythagoras is really just a special case of cosine law. By cosine law, nm squared is 4 squared plus 2 squared minus 2 times 4 times 2 cosine of 60, but that's just 1/2. So this is 16 plus 4 minus 8, and that's going to be 12. So nm is root 12. I guess we can pull out 2 there, 2 root 3. So 2 root 3, not the most helpful. Wait a minute. 2, so 1 to root 3 to 2. Oh, okay, this is a, DMN is a 30, 60, 90 triangle. Nice. That should make things a lot easier, because then this will have to be a 30, 60, 90 triangle. So angle D, it's not drawn appropriately up here. In fact, D kind of looks like right angle, the way I have it drawn. But DNM is 90 degrees, and DMN is 30 degrees. Okay, because we have another 60 degrees up here. And it'd be really nice if I didn't have to do a whole lot of trig, and I could just say this is also right angled. So how can we relate the angles down here to the angles up here? And I think it's because it's a single cut. They do say it's like a single planar cut, right? sliced with a straight cut. So this is sort of like a single plane, which I sort of think of as sheets of paper. So I think if we can make an argument that PQ is parallel to MN, CB parallel to DF. They're going to intersect both at 90, I guess. Is there a more exact way to write it up? So how do we want to write it? So QP is parallel to MN since they are made with a single cut. Okay, it doesn't mean that one is right on top of the other, but they are parallel with regards to sort of the QPMN is sort of like a sheet. Parallel might not be the best word to use. Now, I know CB is parallel to DF. They are right on top of each other. Parallel is not the easiest thing to work with in 3 dimensions, but it is still defined in a sense. They have the same direction. So, MN intersects DF at the same angle as QP intersects CB. Is this true? If they intersect, yeah, they've got to intersect at the same angle, but it's not necessarily true that they could intersect because maybe QP could be above CB. We know it's not in this instance, but just trying to nail down the 3-dimensional geometry. As I said, I'm not the best at the spatial reasoning questions. I could probably introduce some 3-dimensional vectors or stuff like that, but that's beyond high school level, so I try not to use any university knowledge on these contests. I think this is a fine argument. You could probably make a nice little, this sheet of paper is perpendicular to this sheet of paper. At one point, it's got to be perpendicular at all points. But ultimately, that tells us that so angle QPC is 90 degrees, and therefore triangle CPQ is 30, 60, 90. Alright, so redrawing the picture again. I'll draw it with orange because I think we need a bit more boldness here. The challenge will be to show this point G, because I think everything's working out up here. We've got 8. We've got 4 and 2, and I guess we've got 4 root 3, although I think that's more just along for the ride right now. And this is a right angle, even though it really doesn't look like it. This one looks more like a right angle. And we've got C, P, Q. So because it's a 30, 60, 90 triangle, so we see CP is going to be a half CQ, so it's 4. And I guess PQ is going to be a half, not a half, it's going to be root 3 times root CP. So that'll be 4 root 3. So it's twice this smaller triangle down here. We've doubled everything up. Now, is it enough just to say they intersect at some common point G? I don't think that's enough. So I think we should probably talk a bit more about it. So if we think about it, we want to show that a triangle MD where the slope is sort of increasing by, is going up by factors of 2. Now, how do I want to say this? I'm not entirely sure. Okay, let's extend CD, and I want to say there's a point G where they intersect. I don't know if that's entirely clear. So consider the point of intersection with CD and the extended line MQ. Such a point will exist as both CD and MQ lie in the same plane. I don't like using the word plane on a math contest because I think that's more of an advanced concept. But basically, they both lie flat against this side of the triangular prism. So they're going to intersect just like any two non-parallel lines in any fixed plane. The one we're usually familiar with is the Cartesian plane intersect. So that's the reasoning. So we're going to call that point intersection G. So now we're going to get D16, C, 8, 4, and G is X, we're going to say. And this is a right angle. So, by similar triangles, and this is similar triangles, I don't really think we need to make that argument. QC is parallel to MD, if you need to make that argument. But 8 over 4 is the same as 16 plus x over x. So 8x is 64 plus 4x. So 4x is 64. X is going to be equal to 16. Okay, yeah, 32 and 16. Okay, that makes sense. So now we're going to do the same thing. We're going to call the point H, but since DG and DH will both be 16, which I think is what we're going to show. I mean, if it doesn't, I'm going to recheck my calculations and re-understand this concept. Maybe I've done the whole thing wrong. But the idea is we're now going to extend PN so that it intersects CD. Again, same intersection will occur because they sort of lie on the same flat side of the triangular prism. We'll get some point H down here. And it will happen that it's also HD is 16, so that means D and G will coincide, and we'll have our tetrahedron, and we'll know its complete height, and its base is going to be CPQ, which I think we can calculate thanks to that right angle, and then we chop off the other top point, which has a base of DMN, whose area we can calculate because of the right angle. I think we can do this. I'm really hoping that... So I'm going to, rather than have to repeat that argument with the plane, I'm going to say likewise, CD and PN intersect at H. And so it's 4, it's 2, it's 16. We'll call this Y. But you can already see it's the same ratio, so the whole thing is going to be the exact same. This is N, this is P, and this is C. So by similar triangles, 4 over 2 is the same as 16 plus Y over Y. And from there we get Y is 16. 4Y is 32 plus 2Y, so 2Y is 32, Y is 16. But DH equals DG, which is 16. So G and H are the same point. I think this is something that would probably have to be proven. therefore, DCPQ is a tetrahedron. Now, let's get into the volume calculation, which is what we're here to do. So volume of DMNCPQ, I don't really care about the order here, is the volume of GCPQ minus the volume of GDMN. That I think is clear. So these are 1/3 area of base times the height of 32 minus 1/3 area of the base, which is DMN, and this one was CPQ, times, and now the height is just the 16 up here. Okay, gonna have to finish this on the other side, I think. But volume of DCPQMN is 1/3. Now the area is 1/2 4 times 4 root 3 times 32 minus 1/3 area of the base is 1/2. No, it's not 4, it's 2. 2 times 2 root 3. Times 16. Okay. So let's clean this up a bit. 2 and the half cancel out. Half and the 16 there. So bring out the 1/3, bring out a 16. We'll have 4 times 4, so that's 16 root 3 minus 2 root 3. So that's going to be 1/3 16 times 14 root 3. I would keep the root 3 on top. Don't divide the 3 and the root 3 to get a root 3 on bottom. It's less elegant. We want to rationalize it. We try and keep the denominator as integers, positive integers specifically. But you can say, well, what's 16 times 14? They're both 1 away from 15. 15 squared is 225, so 225 minus 1 is 224. 224 root 3 over 3, and 224 is not divisible by 3, so there's nothing we can do there. And I'm saying at long last, this is over. Okay. So, that should be our answer here. And what exactly did we do for this? And okay, we've gone too far. So, I was initially drawn to the DMN because we have enough information there to finish off this triangle. And you should suspect it's got to be related in some way to CQP. We talked about a single cut and parallel lines there to make that relationship more known. But if it wasn't, they would have had to give us things like what is CP in order to finish this question, because we did not have enough just to start calculating things willy-nilly. So we realize we can get one triangle, we can probably get the other triangle, and then now our thoughts turn to, we have a lot of information, how can we use this information to start figuring out the volume? Okay? And so from my experience of having practiced other contests, I realized, well, this volume is weird. I don't know what to call this shape. I don't know how to start calculating its volume. But it's a Waterloo contest. Odds are it's some well-known figure minus some other well-known figure. Okay, and you could say, well, maybe I don't remember the area of a tetrahedron is 1/3 base times the height. And that's okay, but this is a nice little pattern, like cones, 1/3 area of circular base times height. And same with pyramids and all that sort of stuff. So it's not something that's unreasonable for you to know. If you didn't know that, then maybe you should spend a little time learning about surface areas and volumes for some of the more common shapes and figures. But so I've got it in my head. I know, I should try and recognize it as some shape minus another shape or a couple shapes added together. And it just made sense to me that since CQ goes from 8 down to 4, that we keep going and we'll meet at a point down there at the bottom. and so it should be tetrahedron with the little top tetrahedron cut off. I still had to show it, and I think you probably needed to show that G and H were the same, and that they were both 16 away from D. Otherwise, you wouldn't have the same intersection point, you wouldn't have a tetrahedron, you wouldn't be able to use any of those formulas. So I think that was crucial. And I'm glad I took the time to prove that G and H are the same point. And then after that, area of tetrahedron, it became quite clear afterwards. So it was an involved question. I'm fairly certain I did it all right. Maybe I'd like to see what their argument was for showing that QP hits at the same angle as MN, that it's right angles, that CPQ has to be a right angle. I wonder if they used a vector comment or something like that, because I don't think that's fair at that point. But maybe they used parallel ones. I don't know. I'll look it up. But yeah, once you made that connection, I think it was all clear. I've liked the 2009 paper. I mean, I'm not the biggest fan of these spatial geometry questions, but we faced it together, you and I, and there we go. So we're all done, and the next Hypatia will be the 2010. The next contest I do, I believe it'll be the 2009 Euclid. I will see you guys for more math contests in the future. Thank you guys, as always, for watching. So long for now.